Every square full-rank matrix has an inverse, but rectangular matrices and the rank-deficient matrices have none. So are they stuck forever without an inverse? No. It turns out there is a best possible inverse for any matrix, and the singular value decomposition, the SVD, makes building it almost suspiciously easy. The hardest object in linear algebra hides inside one tiny diagonal matrix. To see why this works, look at what the singular value decomposition hands us. Any matrix A factors as U times sigma times Y transpose. U is n by m and orthogonal. V is n by n and orthogonal. Sigma is n by n diagonal, carrying r non-zero singular values. Sigma 1 through sigma r with zeros everywhere else. Sigma is the simplest example of a rank R matrix. All the structure of A is captured by these three clean pieces. Orthogonal matrices are a gift. An orthogonal matrix has perpendicular union columns, so its inverse equals its transpose. The inverse of U is just U transpose. The inverse of V is just V transpose. No computation, no division. That means the hard part of inverting A cannot live in U or in V. The entire difficulty is concentrated in one place, the diagonal matrix sigma. Invert sigma and we have essentially inverted A. Building sigma plus, the pseudo-inverse of sigma, takes just two mechanical moves. First, invert each non-zero singular value. Sigma sub I becomes 1 over sigma sub I. Notice that we invert only the non-zero values. The zeros stay zeros because we never divide by 0. That's the whole trick that makes this construction work, even for rank-deficient matrices. Second, transpose the shape. If sigma is m by n, then sigma plus is m by m. The reciprocals sit along the diagonal, surrounded by blocks of zeros. Let's take a concrete example. Let sigma be a 3 by 4 matrix with sigma 1 equal to 4 and sigma 2 equal to 2 on the diagonal. The rank is 2 and everything else is 0. Step 1. Invert the non-zero entries. 4 becomes 1/4 and 2 becomes 1/2. Step 2. Transpose the shape, going from 3 by 4 to 4 by 3. So sigma plus is a 4 by 3 matrix with 1/4 and 1/2 on the diagonal, and all remaining entries 0. 2 moves and we're finished. Now here's where intuition usually trips us up. Let's check the two products. First, multiply sigma times sigma plus. With our example, 4 times 1/4 gives 1, and the 2 times 1/2 gives 1. The result is a 3 by 3 matrix with 2 1s on the diagonal and a 0 in the third slot. So this is diagonal 1, 1, 0. Notice that it is not the identity. Now multiply the other way around, sigma plus times sigma. That product is 4 by 4, again with 2 1s on the diagonal and the rest zeros. So it's diagonal 1, 1, 0, 0. A different size and also not the identity. Both products have exactly R1s where R is the rank, but they live in different spaces. Why aren't theirs the identity? Because they're projections, not inverses. Sigma times sigma plus is m by m and it projects onto the column space. Sigma plus times sigma is m by n and it projects onto the row space. Each one keeps the directions where the matrix actually acts, and it discards the null space directions, the zeros. A matrix with a null space cannot have a true two-sided inverse, so these projections are the closest thing to the identity that the null spaces will allow. Now let's assemble the full pseudo-inverse. Start from the decomposition, A equals U times sigma times V transpose. To invert a product, we reverse the order and invert each factor. So A plus equals the inverse of V transpose times sigma plus times the inverse of U. But here's the beautiful part. V is orthogonal, so the inverse of V transpose is just V itself. And U is orthogonal, so the inverse of U is simply U transpose. Everything collapses cleanly to A plus equals V times sigma plus times U transpose. The transposes fall out for free precisely because U and V are orthogonal matrices. All the real difficulty stayed quarantined inside sigma plus, which we already built. Looking at the sizes, V is m by n, sigma plus is m by m, and U transpose is m by m, giving a final result that maps from m-dimensional space back to n-dimensional space. One subtlety remains, and it needs a careful eye. Suppose we try to stuff random numbers into the zero blocks of sigma plus. Write sigma in block form as d in the top left and the zeros elsewhere, where d holds the non-zero singular values. The minimal sigma plus is d inverse in the top left corner with clean zeros everywhere else. Now bloat it. Put a random block B in the top right, a random block C in the bottom left, and a random block E in the bottom right. Let us actually multiply sigma times this bloated sigma plus. The result is the identity in the top left, the block D times B in the top right, and the zeros along the bottom. Here is the key point that the original story got wrong. The bottom blocks C and E do multiply against the zero rows of sigma, so they truly vanish, contributing nothing. But the top right block B does not vanish. It gets multiplied by D and survives as D times B. So bloating that block genuinely changes the product. A quick example makes this concrete. Take sigma equal to 2 in the top left and the zeros elsewhere. Put a random number, call it x, in the top right of sigma plus. Then sigma times sigma plus comes out as 1 in the top left and 2 times x in the top right. That is not the clean identity block unless x is 0. So we cannot just claim every straight entry disappears. This is exactly why minimality cannot rest on the projection product alone. The full set of Moore-Penrose conditions is what pins every one of these extra entries to 0. Those 4 defining equations force B, C, and E all to vanish, leaving the clean minimal sigma plus. That clean version is the pseudo-inverse, unique, carrying no dead weight. Minimality is an optional decoration. It is built into the definition by the Moore-Penrose conditions themselves. Step back, and the pseudo-inverse isn't a patch. It's the natural completion of the inverse idea. When you try to solve A times X equals B, and no exact solution exists or infinitely many do, A plus times B returns the minimum norm, least squares solution, the single best answer. The deeper lesson, every matrix, no matter how degenerate, has a clean 4-subspace structure. The pseudo-inverse reverses the action wherever reversal is possible in the row and the column spaces, and gives up gracefully where it isn't in the null spaces. The singular value decomposition isolated all the difficulty into one diagonal matrix. We inverted only the non-zero singular values, and the orthogonal factors handed back their inverses for free. That construction is the foundation behind least squares, data fitting, and the modern numerical computing. The inverse that always exists.